So, hello everyone. I'm Priya Hassan. I'm a professor in physics and astronomy at the Maulana Azad National Urdu University, which is located in Hyderabad in India. And today I'll be talking to you about this review paper, which is on exoplanets, the past, present, and future. So, by definition, an exoplanet or an extrasolar planet is a planet outside our solar system. So, the first step is to look for exoplanets. How do we actually look for them? And that's what's basically described in this paper. The paper basically describes different techniques or methods which are used to detect exoplanets, and that's what I'll talk about. So, first of all, the question is, why do we look for exoplanets? And this would be, just putting this in just as an inspiration quote to everyone. This is the famous quote given by Carl Sagan in the movie and the book Contact, where he says that the universe is a pretty big place, and if it's just us, it seems like an awful waste of space. So that would be, I'd say, the driver in actually looking for exoplanets, and why are we so convinced that we should have exoplanets as well as habitable universes in, which we need to find. So what are the different planet detection methods? There are many different planet detection methods. It's an old plot, this is 2012, but this very well describes the different methods which are used, from dynamical effects, timing techniques, microlensing, photometry, miscellaneous. I'll be talking about each of them in more detail, but obviously there's a difference in the kind of sample or the kind of exoplanets you detect using different methods. So briefly, the detection techniques are, there's the popular technique of radial velocity. There is one which is using transit photometry. There is microlensing, and there's direct imaging. These are the four techniques I will talk about today, which are also discussed in the paper. Now, if you actually see till the year 2020, you see that there has been a distribution of the techniques which had been used. Earlier, it was essentially a lot of radial velocity, because that was the method that was available. And then by the time Kepler got launched, that was a satellite mission, a space telescope, which is basically looking for transits. You can see that now the contribution from transits with Kepler and then followed by TESS, you now have a larger contribution coming in using transit method compared to radial velocity. But still, essentially, radial velocity and transit are the two most important methods. You also have other methods like microlensing, imaging, but they are obviously much lesser in contribution compared to the other ones. So let's first of all start off with the radial velocity technique. The radial velocity technique is essentially using the effects of gravity. So for example, if you have a star and a planet, they are both going around their common center of mass, which you can see over here. And because of that, you basically have a wobble in the star's position, which also means a wobble in the star's velocity. So if you were observing the spectrum from the star, the spectrum would be redshifted, and would be redshifted while it's going away from us, blue shifted while it's coming towards us. And based on that, you can actually detect the presence of the planet. So another nice graphic showing you that if you were to actually look at the spectral lines, here you can see the spectral lines. The dotted lines are the lab values for the spectral lines. And you can clearly see that there is what is called a red shift, and there's a blue shift in the position of the spectral lines as the star is going around its common center of mass. So in this case, you are not detecting the planet is too small. You are just detecting the wobble or the change in the velocity of the star as it's going around this common center of mass. And this shift is basically what is being measured. Now, like I mentioned, this shift is basically the Doppler shift, and obviously it depends upon the ratio of the star and the planet, because that will tell you how do you see the actual wobble. If you were to see it in case of Jupiter, for example, it barely gives a variation of 13 meters per second. Earth, if you were to observe it, it would give you a variation of only 0.1 meters per second. And therefore, it obviously is very dependent on the sensitivity of your detector. So on the ESO 3.6 meter telescope, the HARPS instrument has a measurement limit of about 1 meter per second. So you would easily be able to detect a Jupiter-like planet using HARPS. And this is exactly what is used by the Geneva team when they measured radial velocities using HARPS. And I'll come into a minute into the generic theme. But essentially, the problem in the radial velocity technique is that you are only going to see the component of velocity which is along your line of sight, right? And therefore, you are only seeing that projection. And there was a question also on Piazza on why is it the lower limit. That's because you are only seeing the component which is in your line of sight. And supposing if so it's essentially an M sin I kind of component. So supposing if the velocity was only in the plane of sky and nothing in the line of sight, you would not see any line of sight because your sin I would be 0. You would not see the component. And essentially because you're only seeing this component, the formula is essentially this, and you're only seeing that component, so that would limit the mass that you would be detecting. So that's the lower limit. Now, a bit of history, the first exosolar planets were basically found using pulsar timings, which is now not so popular, but essentially that was used earlier. And the first exoplanet around solar-like stars was detected by Mayo and Quillitz in 1995, for which they got the Nobel Prize. And this was 51 Peg, the exoplanet, which was detected using radial velocity technique. So that's exactly what Didier and Quillitz got the Nobel Prize in 2019 for the first detection of the exoplanet around a sun-like star. And this is using the radial velocity technique. Here you have both of them. And you can actually, essentially what you're doing is you are measuring the delta lambda by lambda, which gives you the V by C. And like I mentioned earlier, the V is the projection in the line of sight. So that is dependent on the resolution or of the spectroscopic instrument which you are using. Now, the future telescopes, for example, the extremely large telescope the Codex instrument will give us a superb capability of 2 centimeters per second, which would mean that you would obviously detect even Earth-like planets using that kind of an instrument. But this will come with the European ELT. The present instruments, like I mentioned, give you about a 1 meter per second, thing like that, and that's our present capability. The disadvantages of radial velocity is that you could also have such a shift coming because of various other effects. For example, you would have false signals coming because of multi-planet, multi-star systems. If that could also give you the wobble. There could be stellar activity or magnetic fields which could actually give you this kind of a wobble. And therefore, what's very important, which was even in the work done by the Geneva group, was actually calculating the effect which you could get from all these effects, multi-planet, multi-stellar, stellar activity, etc., to rule out all those false positives, and then finally attribute it to the presence of your, of the planet that could give you the system. So the other popular method which is used is the transit method, which is a very simple method in the sense that if you have the planet coming in front of the sun, you will have a dip in the brightness of the light coming from the star, and that is called the transit method. But the transit method, like you can see, is that it obviously depends upon the ratio of the squares of the radii of the two, the planet as well as the star. So for example, if you were to take it for the Sun-Earth system, you take the ratio of the radius of the sun to the radius of the star, you would see that the ratio is about 10 power 4. And therefore, the kind of precision in the photometry which you would require would be less than 1%, right? You need, because this dip over here is exaggerated, you can see a large dip, but essentially the dip is something very small. So for example, if you had 1,000 light bulbs, if one of the light bulbs was switched off, you should be able to detect that. And that is the kind of precision you will require in your photometry if you want to detect it, right? So that is the problem with the effect if you're using transit photometry. But for example, we'll come to that in a bit. If you have your photometry from space, then you can look for that kind of a precision, and that's exactly what Kepler and TESS achieved in their data, right? Now, the other method which is used is the micro-lensing method. Essentially, what that means is that if you have a lens star orbited by a planet, what you would have is, because of the gravitational lensing effect, you will have multiple images being formed. And if you have multiple images being formed, you will have a variation in the brightness of the star. And that is the exactly variation which you are trying to look for. But obviously, getting this kind of a variation for this perfect alignment to take place so that you can get this kind of an effect. It was actually calculated by Brzezinski, which is a chance of 1 in a million. So it's a very it has a very low probability. It's a low probability event, as well as it will not get repeated, and therefore it's a little bit of it's a difficult event to find. It has been used by various surveys, the Macho Eros Ogle survey, which actually looks for it, but it can detect mass and orbital distance without ambiguity, can detect very low mass exoplanets, and it can also be used for looking for exoplanets in other galaxies, for example, in M31. The other technique which is used is the direct imaging technique, but it's obviously very difficult because the star is going to be much, much brighter than the planet, and therefore, because of the contrast, which could be even a factor of 10 power 9, a billion times, it would be very difficult to actually detect it. And for example, Jupiter's Sun at 5 parsecs, the angular separation is less than 1 arc seconds. It's very difficult to actually detect it. So what is the way of doing it? The simple way of managing this thing is, for example, if you want to look at the sun, right, the corona of the sun, the typical method used is to use a coronagraph. That is, you block out the light coming from the star. And that's exactly what is done, is you actually, if you want to look at the star and you want to see the variation in the brightness, this is the planet coming in front, you close or you cover the star so that you can see the brightness coming from the planet. And that's exactly what is done by various instruments, which are detect imaging instruments, for example, on the Keck telescope, or you can see an example here of a VLT image of a hot young planet around a brown dwarf star, or even the HST, the Hubble Space Telescope, uses a coronagraph to actually look for planets around the star Fomalhaut. So these are techniques which are being used. They are a little complicated, but they are effective in actually getting that. So you can see that, for example, for this star, you can actually detect the 3 planets which are there, and you can, they have been done. Beta Pictoris is another planet which is being this thing, which again would be used using the VLT, the Very Large Telescope. Could actually use, put a coronagraph to actually then detect the planet. Effective planet hunters are space-based telescopes. These are using the transit method. Like I mentioned it earlier, you need very high precision, and therefore Kepler telescope was dedicated just looking for planets. It was launched in 2009, and it basically looked for, it's a Schmidt-type telescope with a 0.95 meter aperture, with a 1.4 meter telescope looking for these things. So it basically looks at a certain part of the sky and looks for variations in the brightness of stars. There have been various exoplanet missions. In a way, Hubble and Spitzer also have been used for looking for exoplanets, but Kepler and TESS are dedicated missions specifically meant for exoplanets. The James Webb Telescope, as well as Plato, is also going to look for exoplanets other than the other programs which they actually have. So the Kepler mission basically looks at a particular field of view of the sky and actually looks for variations around it. Kepler data is freely available, so you can actually do projects looking for Kepler data and looking for light curve analysis of stars and characterizing the exoplanets using Kepler data. This can already be done by you. There was a problem with Kepler, which actually happened because of the reaction wheels in 2013, but there was a solution got to this, and the following mission was called the K2 mission. There was a question in K2 in Piazza on the K2 mission. So basically, the effective wheels now on Kepler are only 2 reaction wheels, and therefore the third wheel was actually, the precision was used by solar pressure, due to which there was a slight change in the kind of the work being done using Kepler now, which is now called the K2 mission, because the third reaction wheel is being replaced by the light pressure which we're getting from the sun. And in that way, you can actually balance the thing. The idea is you need very high precision alignment also for the spacecraft, which is achieved using the reaction wheels. So you use the 2 reaction wheels as well as the light pressure. I will answer the question in more detail in Piazza, and we can continue the discussion on that. The follow-up to the Kepler mission, which is now not functional, in 2018 it was off. You had the TESS mission, which was launched in 2018, which is a follow-up of the Kepler mission. And even test data is freely available. We'll have a session on how can you use test data again to look for exoplanets and follow up with that. What we find is that there are various planet types which are detected using different methods. There are gas giants, super Earths, terrestrial-like planets, as well as Neptune-like planets. And what is done is using various techniques, we try to characterize exoplanets. And so you basically characterize them using various parameters. For example, here it is using the size as well as the orbital period, in which you can characterize different kinds of exoplanets, the hot Jupiters, the cold giants, the rocky planets, etc. You could also characterize them using the radius of the planet as well as the orbital period using various techniques. And they gave us various information about them. For example, the Jupiter-like planets, the Neptune-like planets, the Earth-like planets. Like I said, it also very sensitive to the kind of methods used to detect them, because some methods are more effective in finding different kinds of planets. Another important thing is you actually would like to see the planet size and compare them with Earth sizes to get it like this. A very important parameter is the radius versus mass, because that gives you an estimate of the density of the planet, which gives you an estimate of the composition of the planet. So if you actually have a handle on the density, you can actually talk about what kind of a planet you are actually looking at, and that's what people try to infer from the data you get from exoplanets. And another important thing is the atmospheric composition. So what is done is called transmission spectroscopy. And Hubble and Spitzer have been used effectively to actually look for the atmospheric composition. And the James Webb Telescope, which will soon be online and be in functional mode, it will also do the atmospheric composition, essentially using targets which are found by Kepler, TESS, and other missions. So then James Webb can actually do targeted surveys of the atmospheric composition of certain shortlisted exoplanets. And another important thing I wanted to point you about is that in the orbital distance also, Kepler has found about 30 exoplanets in habitable zones. We basically look for planets in habitable zones because that's where we'll actually look for life. But there's another important factor that you could also have planetary migration. Planets could actually migrate in and out of the system. So they could be formed at a different location and then they move. And therefore, there's a lot of interesting research being done on how actually planets are formed, at which positions, and then how do they migrate. Because we know that migration has even taken place in our solar system. Jupiter is not exactly where it should have formed. And that's also a very interesting thing to study with planetary studies. As well as there are also more complications to these problems. First of all, looking for multiple systems. For example, if you're seeing a transiting planet and you have a multiple amount of planets for that star, you could actually have different dips corresponding to that. And then there's also a new, very interesting field of actually looking for free-floating planets, which is something that is also very interesting, but cannot be, which is more difficult to handle. But that's also an important piece of research. So I'll end with this. And I would say that we have a lot of exciting times ahead with data from Kepler, TESS, and then other data which will come in, which will be using extremely large telescopes, including James Webb, as well as the ELT, the TMT, and the GMT. So we do have very exciting times ahead with more work being done. Thanks a lot.